You know how we're a math and stats podcast? Well, one of my favorite things to do at a cocktail party is to challenge myself to tie math back into whatever conversation we're having.
Oh, that's good. I'll use that the next time I'm trying to exit a conversation.
But it's fun! Making people see math everywhere also keeps them from feeling intimidated by the subject.
I'm really not particularly what I would think of as a mathematician by any stretch of the imagination. I have over the years worked with many excellent mathematicians, people in applied math, physicists who are much better at climate theory than I am. But the tools of the trade are very useful, very broadly applicable.
Wait, I thought I was supposed to be the one who isn't a mathematician.
Well, we're the hosts, so I think we get to make the rules. And I think it's important to understand that math is an important tool in our toolbox whenever we're trying to tackle a particularly difficult problem.
Well, based on our previous experiences, climate modeling definitely falls under the complex problems umbrella.
Which is why Matt Huber, a professor in the Earth Atmospheric and Planetary Sciences Department at Purdue University, has worked so hard to make sure that he's learned the mathematical tools to tackle modeling ancient climates as a way to understand what our future climate might look like.
I'm a climate modeler, so I look at past climates and current climate and try and understand what future climate will be like.
Okay, I know we want to jump right into the models that Matt is talking about, but I think we have something to do first. Introductions.
Right as ever. I'm Sadie Witkowski.
And I'm Ian Martin.
And you're listening to Carry the Two, a podcast from the Institute for Mathematical and Statistical Innovation, aka IMSI.
This is the podcast where Sadie and I talk about the real-world applications of mathematical and statistical research, even in fascinating instances where a non-mathematician is using math to solve some really important problems.
We might seem like an odd couple to tackle these topics. I'm a cognitive neuroscientist, and Ian is a high school choir teacher. But it turns out you don't need an advanced degree to learn how math and statistics connect with the world around us.
And for the months of May and June, we're collaborating with the American Geophysical Union's podcast, Third Pod from the Sun, and talking to some lovely climate researchers.
So, if you enjoy this conversation, you should check out the AGU's podcast this Friday. And don't worry, we'll make sure to link to their podcast in the show notes.
Now, back to Matt's modeling work.
Well, before we talk about modeling the ancient climate, I think it's cool to hear a bit about how the history of climate modeling comes into play. Turns out, when we're trying to model the future climate, we rely on a big set of equations to do so.
So this is the same set of equations that we use in weather models that come to us really from going back in time. They come to us from Wilhelm Bjerknes, who is a physicist coming out of the, kind of grand age of physics in the last part of the 19th century and the beginning of the 20th century. And he realized that you could write Maxwell's equations and kind of tweak them a bit to represent fluid motions of Earth's atmosphere. And he wrote a foundational set of papers starting in 1905, which really took atmospheric science from being a statistical discipline to a physics-based one. And Wilhelm Bjerknes' son, Jakob Bjerknes, was a very famous atmosphere-ocean scientist who has given his name to the Bjerknes feedback, which is one of the important parts of understanding El Niño.
Maxwell's equations, aren't those the ones that describe how electromagnetism works?
Yeah, it's a set of coupled differential equations that explain electromagnetism and classical optics and other important stuff.
I never thought about how people in the early 1900s were trying to answer some of the same questions around weather and climate that we are today.
Right? Although these initial attempts by early researchers were iterated on and became more complex with the use of computers for some of those calculations.
So there's a long history of really kind of late 19th century, early 20th century physics informing a set of equations that would eventually be solved on computers. And we just keep adding more and more of these equations, the geophysical fluid dynamics equations on a rotating sphere, to which we add radiation We try and represent turbulence as well. So the whole field of turbulence is somehow embodied within atmosphere and ocean science, which we need to do in order to model the climate system. So you kind of have these simplified models, just 3 equations or 5 equations or 6, versus trying to solve the full set of equations, for fluids, turbulence, radiation, and you have to do it grid cell by grid cell. So we do these numerically, and each set of equations, there'll be millions of equations that are solved at each time step. And we march forward in time with those in the form of a general circulation or global climate model.
Oh, God, this just sounds so complex. From just a handful of equations to millions? No wonder they needed computers for this.
But turns out a more complex model isn't always more accurate.
Really?
Sometimes those simpler models seem to represent reality better than the most sophisticated models, the ones with all the terms of the equation, which is a little bit counterintuitive, because you would think that as I write more and more terms in an expansion, or when I add all of the nuances and details to the equation, we might think that the behavior becomes more accurate. And that is the case some of the time. But in terms of these major transitions in the climate system, it's oftentimes the simpler models where we've reduced the number of equations and we've reduced the number of processes that we're including that seems to capture those better.
Wait, do we know why this is happening?
Not totally, at least not yet.
So it's a bit of a conundrum. The community of people working on these sophisticated Earth system models kind of keep going around on this. Do we want to add more complexity, or do we want to capture the essence of it? And the coin of the realm is, well, which matches reality better?
So what are we missing to make this modeling better, with or without complexity?
We really need paleoclimate data to extend the length of the record to validate and verify these model formulations.
Basically, we should probably be looking further into the Earth's past if we want to understand where we're going on those big geologic timescales.
Okay, sure. But how do we do that? How can we know about the truly ancient climate when we didn't have thermometers back then?
Turns out there are a lot of clever ways that we can know about our past climates.
Yeah, there's a wealth of paleoclimate data that's available. So people might be familiar with ice core records. You have scientists who go down to Antarctica or to Greenland or to small ice sheets in the tropics and drill into them and collect long ice core records, some of which can resolve changes in climate down to individual years, but perhaps more frequently tens of years of resolution. But they can record climate over tens of thousands to a million, or a little bit longer than a million years. And those records, you can think of it as like a tape recorder or something that's just kind of every layer of snow that comes down takes a little snapshot of the atmospheric composition, so the amount of greenhouse gases like CO2, and also the isotopic composition of the air or of the snow itself, which tells you something about temperature.
So that's one method using ice. We can also use a similar technique in our oceans as well.
We have similar technologies that are used in the deep sea. So people go out on scientific drilling vessels and take cores that can go back 60, 80, 100 million years. And not with the same temporal resolution. So you're not getting, typically year-to-year variability, but you might get centennial scale variability in the climate system.
And finally, we have fossils here on land that we can collect information through as well.
And on land, we have geological records as well. So you find fossil leaves, and that tells you a lot about what the climate was like. You can also use fossil leaves to tell you what the atmospheric CO2 concentration was. And we have geochemical fossils as well. So plants or animals make their bodies out of lipids we can use various techniques using isotopes to reconstruct temperature from the waxes or from the fat, essentially.
Wow, this somehow involves a lot more paleontology than I expected for a climate change episode. And also, the information they can glean from the smallest and most random things, it's wild.
Yeah, so using these techniques, we can build a pretty clear idea of the major shifts in our planet's climate. And those shifts sometimes happened extremely rapidly.
So for the past couple million years, the Earth system has been oscillating between glacial and interglacial states. So the most recent one being the last glacial maximum about 21,000 years ago, where you have, famously a mile of ice above Chicago. The climate system can get very cold, and those are called glacials. And then we have interglacials, where the world warms up substantially, and we've been in an interglacial now for the past 10,000 years. The behavior of the climate system coming out of the glacials and into the interglacials can be, very rapid transition. You tend to stay in the glacials for a long time, so roughly 100,000 years or so. But the transitions out of them can be very, very rapid. And the whole system seems to transition at the same time. So you have warming, you have CO2 increases in the atmosphere, methane increases in the atmosphere, changes in dust, changes in the ocean circulation.
This sounds like something out of The Day After Tomorrow.
It's funny that you mentioned that.
If any of you have seen The Day After Tomorrow, that movie is very loosely based on what happened during the Younger Dryas event. So you're coming out of a glacial period, a very cold period, and the world was warming, and then there was a hiccup, and the planet really abruptly cooled substantially for a couple hundred years due to a change in the ocean circulation. And then it started warming up again.
Here, Matt is referring to the Younger Dryas event, which happened about 14,500 years ago, right as we were coming out of our last glacial event and rapidly cooling off again before actually warming.
I'm assuming you mean quickly for geologic timescales, right?
Yeah, not like it literally happened overnight.
But you said something earlier about how the complex climate models we tend to use these days aren't good about rapid changes. What's that about?
The big computational Earth system models I was talking about get roughly the changes right, but they don't get the rapid transitions and the highly nonlinear behavior as well. And that's really been kind of the stomping ground of these simplified models.
So, do we know why the more complex models aren't catching the rapid shifts?
Well, Matt does have a few thoughts on what might be causing it and how we can use the information we learn about our ancient climate to better inform models. But
Don't tell me you're not going to explain until after the break.
wow, look at your 100% prediction accuracy.
Thank you. But also, we'll be right back after this message.
If you're getting a lot out of the important research shared on our show, there's another University of Chicago Podcast Network show that you should check out. It's called Capital Isn't. Capital Isn't uses the latest economic thinking to zero in on the ways capitalism is, and more often isn't, working today. From the debate over how to distribute a vaccine to the morality of a wealth tax, Capital Isn't clearly explains how capitalism can go wrong and what we can do about it. Listen to Capital Isn't, part of the award-winning University of Chicago Podcast Network. So, as a quick recap, Matt is interested in using observations of paleoclimate records to understand our climate's past and help predict where our current trajectory may be taking us.
Oftentimes, they have interesting properties that beg explanation. And we use a hierarchy of models in order to understand those interesting behaviors. Many of the more sophisticated models, which are many of the ones that I used, developed by major national modeling centers. They are physics-derived equations, or they're derived from physical equations, and they run on massive supercomputers that generate hundreds of terabytes of data. They take years to do a single simulation. Those are a very important part of our toolbox.
But you mentioned earlier that sometimes the simpler models do catch these fast shifts.
Simpler techniques, really, almost toy models, if you will, or slightly more sophisticated than toys. But low-order dynamical systems models seem to capture the transitions in paleoclimate records better. And, that kind of really raises the question. We tend to not use those simplified low-order models looking into the future. So if the simple models seem to capture transitions better, rapid change better, does that raise some questions about what we're thinking about, what we're doing as we are trying to project ahead in future climate?
Oh, but before we go on, I want to explain what toy model means.
I'm assuming it's unrelated to the model trains my dad built as a kid.
Yeah, not quite.
Toy models are great, right? So people use the word toy model when it's a little bit self-deprecating. It's a little bit like saying, listen, I know that I've hugely simplified this system and that it's way more complicated, but I'm going to do something because it seems to produce some interesting and perhaps relevant behavior. That behavior may not, of the simple set of equations, may not match reality perfectly. In fact, it may only match one aspect of reality, right? There may be many things going on, but if it captures the essence of some behavior, we might call that a toy model.
Toy models are really common in all sorts of mathematical fields. I hear visiting researchers at IMSI talk about them all the time.
Well, I'm only a little disappointed that I can't imagine mathematicians sitting on the floor making Lego versions of something like a squared plus b squared equals c squared.
Wow. Just wow.
I wouldn't say this is a fully solved or resolved point. It's a tension. It's an argument that runs through the community, because the data that we're basing this logic that I just described on is also imperfect, and it's subject to both smoothing just through geological processes, which remove information through time, but also through filtering or sharpening. So there may be some things that appear to be very abrupt, but that's simply because some time is missing in the record, or some important slow moving process is not represented in the geological record. So this is just sort of an ongoing dialogue within the community.
Like all the best topics in science, it's still an area that's open for discussion as to why our complex models don't catch these transitions and how we should adjust them to better reflect what has actually occurred in our geologic history,
while still being accurate in predicting the changes we're currently seeing in our modern climate.
Right. So let's look at a specific example to help explain.
The Antarctic ice sheet, we think of this as this big, ponderous, cold place on Earth. It's hard to imagine it not being there. But out of the past 100 million years, that ice sheet has only been there for about 35 million. So 2/3 of the past 100 million years have been spent without an Antarctic ice sheet. And there was no Greenland ice sheet until about 3 million years ago. So, the world used to be quite ice-free. And so that initial period of time, what we call the Eocene-Oligocene transition, about 35 million years ago, is when rather abruptly ice started growing on Antarctica.
Wait, I thought we were going to talk about how our current climate models aren't great at catching rapid shifts.
Hold your horses, we're getting there.
It's actually a classic example of nonlinear systems behavior and having a bifurcation where there's some sort of slow changing parameter. We think it's CO2. So that was just gradually decreasing from about 50 million years ago. And then abruptly there's a transition, which just has to do with that once you get ice sheets growing, they're shiny and white. And so the bigger they get, the less radiation is absorbed, so the colder it gets. So the bigger they get. So there's a strong positive feedback that kicks in, but it can only kick in when CO2 is low enough that you can have an ice sheet. So there's a slow transition, and then boom, the Earth system just rapidly transitions to a new state.
It sounds like our climate shifts are actually happening really fast. Thank you, climate change. So What's Matt's view on this?
I think that the very complicated, sophisticated models that we typically use with millions and millions of equations and every possible physical and chemical interaction operating in them, they're so complicated that it's like training wheels have been put on them, right? So, it's like, just imagine putting a really uncoordinated kid on a very fancy bike. It's going to go all over the place, and that's not the goal, right? So maybe they put training wheels on it, and unfortunately, I think that in many ways, with our most sophisticated models, for a long time there were training wheels on them, which effectively what that means is that they were kind of more or less guided to not transitioning rapidly. Because if you had taken all the time to create this very complicated model and it immediately started looking like Mars or Venus, that would be a problem. So you would go in and make sure that things don't change that much too quickly. And I'm a little concerned that in the process of doing that, of getting those very complicated models to match current reality so much, they were sort of overly tuned to reproduce current reality. And the aspects that allow them to be dynamic and change rapidly might have been beaten out of them a little bit. Whereas with the simpler models, they're under nobody's sat there and told them, behave. They tend to do whatever they want because people think of them as sort of toys. So that's sort of consequence free. So the important thing is that climate modeling is done by people, and people have designed the models to fulfill different purposes.
So basically, Matt thinks we built the complex models to mimic the climate stability we had before climate change?
Yeah, and maybe by fitting the model too closely to those specific parameters, it can't adapt and accurately predict the big rapid changes we'll probably start to witness due to all the CO2 in our atmosphere.
So, instead of the slow changes of the recent past, we might be in for a big change very quickly.
We have just about released enough CO2 that we're going to kick out of those oscillations. So we've just experienced our last interglacial, and we're moving rather rapidly to the state that the climate system was like between 3 and 15 million years ago. And during that period, there was no Greenland ice sheet. Sea level was substantially higher, tens of meters higher. And the climate was between 3 and 7 degrees C warmer than it is today. So we've already added enough CO2 that unless we stop immediately, you can forget that whole glacial interglacial thing. Not going to happen again. We're punching through to a different climate state. And the Earth system has been in that state before. It's not like, we go to Venus or, no. We've been through this. It hasn't been recent. It's been a long time. I'm not saying it's we've done this before. It's no biggie. No, it's very big. We haven't done it in 3 million years.
Ooh, I don't know where to start. The fact that there's no way we're getting the whole world to stop emitting CO2 immediately is leaving me caught between immense despair and complete anxiety.
Yeah, I'm sorry this episode couldn't be more uplifting at the end like last week with Christy Ebby. But I think we have to take a hard look at what we've done to the climate and face some tough news about how quickly it's going to catch up with us. It might not be a runaway train yet, but it's dang close.
It's hard not to hear this and feel at least a bit hopeless, though, especially if these changes really are going to snowball and happen faster and faster.
Yeah, I do fear the consequences quickly headed our way. But we can't prepare for them and try to mitigate their impact unless we have a clear-eyed view on what our future could look like. So it might be hard to hear, but important nonetheless. Don't forget to check out our show notes in the podcast description for a link to Third Pod from the Sun story with Matt Huber. We'll also link to Matt's talk on their research from the Confronting Global Climate Change program here at IMSI.
And if you like the show, give us a review on Apple Podcasts or Spotify or wherever you listen. By rating and reviewing the show, you really help us spread the word about Carry the Two so that other listeners can discover us.
And for more on the math research being shared at IMSI, be sure to check us out online at our homepage, imsi.institute. We're also on Twitter at IMSI_institute, as well as Instagram at IMSI.institute. That's IMSI spelled IMSI.
And do you have a burning math question? Maybe you have an idea for a story on how mathematics and statistics connect with the world around us. Send us an email with your idea.
You can send your feedback, ideas, and more to sadiewit@imsi.institute. That's SADIEWIT@imsi.institute.
We'd also like to thank our audio engineer, Tyler Damme, for his production on the show.
And thanks to Jessica Buser-Young, producer with AGU's Third Pod from the Sun, for their work collecting tape.
And music is from Blue Dot Sessions.
Lastly, Carry the Two is made possible by the Institute for Mathematical and Statistical Innovation, located on the gorgeous campus of the University of Chicago. We're supported by the National Science Foundation and the University of Chicago. Anything else you want to say into the mic?
Good night.
Good night, goodbye. Hi, tie, tie.
Could someone please do this IB training for me?
Okay, bye. Never mind. Sorry. In my head, it sounded a lot funnier.